לא, אפשר גם בעברית. לא בעברית, אפשר גם בעברית. כן, כולם מדברים בעברית.
Anyone needs the software here in English? Huh? English for today. Okay, so
זה הטלפון שלו נגן שם, אנחנו רוצים לקבל שאלה?
I'm not sure what it is. Maybe it's the Zoom password.
כן.
Okay.
כן.
Okay, good morning. We are happy to host Yonathan Efroni today. Coming Yonathan, Yonathan is today a research scientist at Meta in New York, right?
Yeah.
And he finished his PhD at the Technion with Shai Gadol in the field of reinforcement learning, and then he has a postdoc at MSR New York.
Yeah.
2 years.
Yeah.
And then today he is in Meta. Very happy to have you here today, Yonathan. Go ahead.
Yeah, thank you. Thanks so much for your hospitality. Yeah, so hi everyone. I'm Yonathan. Today I'll talk about this line of work, reinforcement learning in the presence of irrelevant information. So a bit oh yeah, it works. That's good. Okay, so a bit about my own trajectory. So I started in Tel Aviv University and I did my undergrad here. And then I moved to the Weizmann Institute, then as Nora said, to the Technion, Microsoft, and Meta. So it's very nice to complete the full circle and coming back here to Tel Aviv. And a bit about my motivation and maybe like my general future wish is to make reinforcement learning and interactive learning applicable. I think that we haven't achieved that yet, and I think that it's interesting and important. How should we do it? There's an echo from my computer. Okay, how should we do it? So I think that as a starting point, we should tackle realistic settings, such as high dimensional settings and partially observed settings and so on. And furthermore, I think that we should have guarantees, provable guarantees, or if we don't have provable guarantees, we should be able to explain stuff or to have develop robust, fair, and safe algorithms. And the way to achieve this is really by joining forces between theory and practice, in my opinion. And indeed, I've done a lot of work that I'm mostly doing theoretical work, but I've collaborated a lot with practitioners as well in the field. All right, so without further ado, let's dive to the talk. Yeah, I'll start by discussing about recent developments that we had in reinforcement learning, and I'll describe what RL is. And then I'll present the main theme of this talk, and then I'll briefly mention some other directions that I was involved in and conclude with some general thoughts. Right, so let's give it a shot. Right, so in recent years, we've seen a lot of great successes in reinforcement learning. From the AlphaGo M0 algorithm that in which that was managed to win the world champion in the game of Go, and to a lot of interesting developments in robotics and RL. And quite recently, in the last months, we saw very interesting two papers that combine NLP, natural language processing, and reinforcement learning to achieve quite impressive successes. Specifically, the GPT chat. I'm sure that you all heard about it, and uses some reinforcement learning techniques. And so, what RL is? So reinforcement learning is, in one sentence, it's a paradigm for learning optimal policies of sequential problems through interaction. By interacting with these environments, we slowly and hopefully surely we learn how we should take actions in this world. Right, so we have an agent takes actions, the agent affects on the world, it gathers reward, and our general goal is to maximize the cumulative reward that we gather. And so differently than in supervised learning, which is more about prediction tasks, in RL we mostly care about our goal, and we want to develop an agent that takes an action, and the agent wants to maximize some long-term goal that it has. And for that reason, I think that RL is interesting and maybe a bit different than supervised learning, because it's more about goals in the world and less about predictions. So maybe we can think about predictions as a proxy to things that we actually care about. Yeah, are there any questions until this point? By the way, feel free to interrupt if someone has any question. Okay, so the framework that underlies reinforcement learning is the framework of Markov decision processes. A Markov decision process, or an MDP, is a general way to represent a decision problem. So the common way to view what an MDP is essentially it's the set of the following things. It has a state space, an action space, transition model, a reward function, and it has the horizon of the problem. And in this talk, I'll think about the horizon of the problem as finite for simplicity. The objective is to find an optimal policy. We care about finding the optimal policy that essentially maximizes for example, the expected cumulative reward, the expected and future cumulative reward, and the optimal policy takes the optimal action from any state that we observe. And indeed, we can also view the game of Go, if we have a fixed opponent, as a special case of an MDT, where the reward function is essentially going to be 1 if our agent wins, and it's going to be 0 if the agent loses, right? And at least theoretically, we can solve this MDP and find the optimal policy, which is the optimal way to respond to the opponent.
Where is the randomness?
Yeah, so the randomness is
In the game.
Yeah, in the game is in these two objectives. So the transition model can be probability distribution, and also the reward can be a random variable. Yeah, that's a good question. Right. So with this framework in mind, we can understand reinforcement learning through a bit of a different perspective. We can understand reinforcement learning as a paradigm for learning optimal policies and an optimal policy of an unknown MDP by interacting with the MDP. Great. So and by the way, in this talk, I will mainly focus about probably approximately correct reinforcement learning guarantees. That is, I will mostly be thinking about the setting in which we ask the following question: how many samples an agent needs together interactively to return a policy pi hat, such that pi hat is near optimal in the standard sense and with high probability. And by saying here interactively, I mean that the agent can interact with the world and change his policy while interacting with the world. So his policy can be a history-based policy. What? What's what? So in this probably doesn't really matter. So it can be either a sample, it can be either a trajectory, so a set of age samples, or as well like a single sample. So they're related to each other by age, by the horizon of the problem, because we think about the simpler finite horizon case. Yeah, so in light of the empirical success that we've seen, there has been a lot of theoretical progress as well in reinforcement learning in recent years. So I'm sure that all of you are aware of that, and there are many that sit in this room that also studied these problems quite a bit. But I guess that now it's safe to say that we almost completely understand sample complexity and regret guarantees in tabular reinforcement learning. We have new results on provable and reinforcement learning with function approximation, when the dimension of the problem might be high and when the problem is non-tabular. We have we have better understanding about what practical algorithms they're being used and doing from, and we have like better guarantees from them. And we have many more interesting developments in recent years. And I was also involved in some of these directions during my PhD. But of course, the natural question here is are we done? And did we solve reinforcement learning? And of course, the answer is no, because otherwise the talk would be ending now. And maybe I'll try to persuade you why that's the case. So let's think about how a standard interaction or standard data gathering process looks like in reinforcement learning, right? So we have an agent, it interacts with the world, it sees the reward. Our data, unlike in supervised learning, it's a set of trajectories, where each trajectory is a long sequence of observations that we see, and actions that we took, and rewards. It's a long sequence of observations. Now, in practice, this long sequence of observations have many challenging problems. So number one, we usually expect to see a high dimensional data and an action space, which is going to be also a high dimensional object. So these observations here, we can think about them as images or a lot of features that we get from the environment. And so that means that most or probably all the tabular results that concern with reinforcement learning in finite state space are quite vacuous. And also, more interestingly, I think that it's also safe to say that in practice, we never really encounter a Markovian problem. It is expected that the problem is not going to be Markovian, it's going to depend on the history, and it's not going to be fully observed problem. For example, if we think about a scenario that the patient interacts with the doctor, obviously the policy that the doctor, or hopefully the policy that the doctor performs, will depend on the history of the patient and not only about its current status. Also, we may encounter in practice unseen data that gives rise to safety, robustness, and risk issues. And we have a lot more problems that we encounter in practice that are not really being considered in contemporary reinforcement learning and in the contemporary reinforcement learning field. Yeah.
Talk about these problems just in theory, or also they also manifested in practice? If everything is solved in practice, then
yeah, that's a good question. So partially observed systems, so these two, I would say that they're not even being solved in practice, or at least it's extremely challenging to solve it in practice. This issue is also not really solved in practice. And maybe the high dimensional aspect of the problem is, but as soon as you tweak a bit the problem that you solve in practice, you may also face a scenario that the algorithm don't really work. So I think it's actually this bullet that is the key problem here, that although we have some algorithms that might work in practice here, if you tweak the problem a bit, then it's extremely hard to redeploy these sort of algorithms. So that's something that's a bit different than supervised learning, maybe.
Okay.
Yeah.
I didn't understand the example about the physician. I mean, the physician does act in a Markovian way, at least my physician, because the history is folded into a document that tells the doctor what's my medical history, and that's it. It doesn't care about anything that's not written there.
Yeah, it's true. But imagine what would happen in practice. In practice, you would want to feed your system not with the representation that we think is the true one, or not to summarize your history into a single document, but we want to give the full history to the doctor. And how to summarize that's a hard problem on its own. Yeah, feel free. Do you want to go inside? Yeah. So yeah, we're still very far, or at least I hope that I managed to persuade that. Yeah. So with that motivation at hand, and let me dive into the main topic of this talk, and reinforcement learning in the presence of irrelevant information. So the motivation for this line of work is the need to solve high-dimensional reinforcement learning problems And the fact that each time that we encounter a high-dimensional problem, there is often some notion of irrelevant information. Irrelevant, or also we call it exogenous information in this talk. And you can think about it as alternatively about this kind of work is trying to generalize results that we have in sparsity, in supervised learning, to sparsity in reinforcement learning, in sequential decision problems. That's another way to think about what we're trying to do here. Yeah, so this talk is, I'll be mostly presenting this paper. I'll also briefly mention some other works that are related to this line of work as well. Also, it's a great opportunity to thank all the collaborators that were extremely important in driving this work. Yeah, so let's think about how high-dimensional reinforcement learning looks like, and how is it different than supervised learning. So imagine a scenario that we have an agent. This agent is placed somewhere in the park, and the goal of this agent is to reach some other goal state in the park. And the agent observes its input through a camera. So it's a high-dimensional object, and it sees picture of the world, actually a video of the world, and it tries to slowly infer how it should reach the goal. So a recurrent theme here in this type of problem is the existence of a lot of redundant and irrelevant information. For example, the movement of the ripples in the pond and the ducks here. We intuitively understand that they're not really relevant for the sake of reaching the goal. The agent can arrive each goal equivalently well without really needing to process this type of information. So hopefully we would like to design algorithms that don't really depend on the presence of this redundant and irrelevant information. But differently than in supervised learning, in reinforcement learning, the irrelevant information is going to be time correlated. Obviously, the position of the ducks in the pond here is correlated between consecutive time frames, and that highlights some difference between reinforcement learning and the standard supervised learning problem. Indeed, this form of noise, of exogenous noise that has some non-trivial time correlation, is ubiquitous in many practical scenarios, especially when it comes to pixel-based inputs.
But if the ducks don't cross the road, then they are relevant.
Yeah, it's true, definitely. So yeah, so the type of so the way that we define what irrelevant information is here in this line of work is information that cannot affect on the agent. For example, movement of clouds. Now, I definitely agree that it's only like a first step, or let me put it differently. If there's some information that is uncontrollable, but it affects on the process that you're trying to manipulate, then we should consider it as relevant information.
How would you know in advance if the information is going to be relevant?
That's a good question, and that's what makes it a bit more challenging, right? But hopefully we would hope at least to get some result that says that all the irrelevant information does not truly affect on our sample complexity or on our ability to learn efficiently. That's something that we would hope to get. Right, so now I'll start to describe this problem a bit more mathematically so we can study it a bit better and hopefully understand it. Right, so again, in this problem, we have an agent. The agent receives observations in each time step, and the observation contains irrelevant information and relevant information. We call the irrelevant information the exogenous state. For example, the position of the ducks, the ripples in the pond, and so on. And the relevant information, we call it the endogenous state. the graphical model of the underlying of this underlying system that we consider here, it looks like this. So we have the endogenous state S, the exogenous state Xi. They generate the observation, the image, and the actions that the agent takes, they only affect on the endogenous part of the state. Whereas the exogenous part of the state is not affected by our actions, and it can be an arbitrarily stochastic process, in the sense that there is some non-trivial correlation between consecutive timeframes. And we also make the decodability assumption, which means that from each observation, we can also infer the latent state, these two latent states. So the decodability assumption says that that the latent state can be decoded from the observations. So exists two functions, phi star and phi star x, which are unknown to the learner. If we would know these things, then it would be a trivial problem. And they can decode, they can perform this inverse mapping. Why we need to make this assumption? Otherwise, this problem would be partially observed or non-Markovian, and that's going to be a much more challenging problem, and we don't really want to tackle this additional complication. And as we see here in the graphical model represents some factorized structure of the transition model. And so let me show the algebraic form of it. So that's essentially like the algebraic form of this graphical model. So we assume that we have some generating process that generates the observation, and the endogenous process is affected by our action, whereas the exogenous process is not affected by our actions. And we assume that this decoupling holds for all the observations. That sort of describes this graphical model. But are there any questions about it?
Yeah. In principle, for the randomness of the size into the randomness of the MVP, right? The transition. The difference here is that they are correlated in time.
Yeah.
So it's kind of a with non-IID transition in the sense, right?
Yeah. Exactly. Yes. Yeah. For example, like that can be fixed. Yeah. Like for example, that this thing is deterministic function, and then you have like a very strong correlation between time steps.
In other words, if they were IID in size, then it would be a standard activity.
Yeah, that would have been a standard, or it would have been like a standard MVP that has like without this part, because we do make like this assumption on the latency. Yes.
So could there be also an edge from S to Z phi?
From here to here? Yeah, that's a good question. So so if there's an error from here to here, then in some sense it means that we can affect on Xi prime. Why? Because we can manipulate S, and then S can manipulate Xi. Now, so it is like an alternative notion of how we would like to define mathematically what irrelevant is, but it's definitely like weaker notion than this notion. This notion really says that you see an observation that you cannot control, and you don't that you can't really affect on it, and that it's not relevant for the sake of optimal control. So it's a bit different notion. We haven't really studied problems that has this error, and of course it's an interesting question how we can do it. Yeah, so a bit more mathematically, a wishful thinking here would be, okay, let's assume that we have some function class, it contains phi star. We can hope, because we understand sparsity and sparsity in supervised learning, we can hope to get this form of guarantee. That is that our sample complexity would degrade only logarithmically with the cardinality of the function class phi. that would be our wishful thinking, or put it differently, we can hope to get some Oracle inequality if we use like the standard language of sparsity. So the question that we after here is whether we should pay an additional price of log phi or an additional price which scales, let's say like polynomially with the cardinality of phi. That obviously would be very, very bad. It would be very bad. Instead, it would mean that the sample complexity degrades significantly. So interestingly, prior to our work, there has not been a lot of work that's been done on this topic. And specifically, I will show next that the current reinforcement learning theory does not capture this setting, and that is, we don't really have any provable guarantees for the setting of reinforcement learning with exogenous noise. And also, I briefly mentioned some failure cases of deep reinforcement learning algorithms that's used in practice. In terms of theory, so how reinforcement learning theory works, especially in high dimension, usually we try to make some structural assumption on the underlying MDP. For example, these are different types of structural assumptions. We can assume that the MDP has finite Bellman rank, or it has finite bilinear rank, or it has finite Bellman eluder dimension. And given this assumption, we try to construct a separate complex and a provably efficient algorithm that has, say, sample complexity that scale with these structural assumptions. So we started this work by showing that these structural assumptions that essentially are the most popular ones. We started by showing that if these structural assumptions do not capture the setting of reinforcement learning with exogenous noise. So specifically, we showed that in the presence of exogenous information, the Bellman rank and the bilinear rank, the Bellman eluder dimension, they may scale with the number of exogenous states. So they may depend on the cardinality of the exogenous dimension. And that also implies that if we just try to use these types of results, we will end up with an upper bound that scales polynomially with the cardinality of the function class. That's obviously something that we don't want, and because it's something that we would hope not to get, because what we know on sparse regression, for example. So about practical applications, we also showed that some practical approaches that are doing state representation learning, they also suffer for some problems. Specifically, we showed that they either over abstract or under abstract. So over abstraction, I think that both are pretty intuitive concepts. Over abstraction, essentially, it means that the representation function phi merges two states that should not be merged. So what happens here? So we see here that the agent is placed in a different place in the part, but phi merges these two observations together. It identifies these two observations as if they came from the same state. Now, the issue with this sort of problem is that the optimal policy cannot be realized if we have an over abstraction problem. And in our work, we show that some popular technique, which is called one-step inverse dynamics, may over abstract. And the dual problem to this problem is the under abstraction problem, in which the representation function that we have actually splits two observations, although they're not different from the endogenous state perspective. So here we see that the agent is placed at the same place in the part. However, because the dot is placed in a different place, the state representation function says that these two observations are different. And the issue here is that we will get too many states that would ultimately lead to slow convergence and would be problematic from this perspective.
So when you say you have a result that the method may under abstract or over abstract, so what, do you like come up with a particular problem where that happens?
Yes.
And how does that problem look like?
So here it's actually So here it's quite generic. It's not like an actual problem. You should only assume that, for example, that the exogenous part of the state space is deterministic, that there is a correlation of 1 between consecutive timeframes. So you need to make some structural assumptions on the probabilities, on the probability distribution. That's what happens here. And in this, to show this result, we need to consider a specific MDP. We can definitely talk about it, but the intuition here is that if you have an MDP which is disconnected, then the abstraction which is built on one-step inverse model cannot really tell whether it cannot really tell whether it's a different MDP or the same MDP if you have two MDPs that doesn't have joint pairs. But let's talk about it a little bit and show the counterexample. Yes, so here it's a very specific graph.
But this is like in a certain parameterized setting, or is this in a tabular setting?
It's in the tabular setting. It's in the tabular setting in the sense that the underlying model is tabular, the latent model is tabular, but the observation can be anything. Okay. Yes.
I have a question, perhaps you address it soon, but these two pairs of examples look very similar to me in the sense that the question is who is more important, the person or the duck? And the question is, are you going to tell your system who is more important?
Exactly.
Okay.
Yeah,
If there's extra intervention by a person, by a user to tell the system who is more important.
Yeah. And these two problems are different, but they definitely, like, the issue is that in the first one, you lose relevant information, and in the latter, you think that something which is irrelevant, you think that it is relevant. And
I understand.
Yeah.
I wondered whether you deduce this automatically or you state this explicitly.
oh, so here we only mention like counter examples for existing techniques. Yeah. So what do you mean by mentioning it explicitly?
You are going to solve this issue, right?
Oh, yeah. Okay, so let's try to solve this issue. Yeah, so we introduced the path prediction and elimination algorithm. It's a very intuitive algorithm. We start with a simplifying assumption that the initial state and dynamics of the endogenous information are deterministic. So that's a pretty harsh assumption. Later, we will also present some extension that we made in which we remove it. But I think it's a very simple and neat algorithm, so why not? I'm showing it. Great. So the thing that the PP, the path prediction elimination algorithm, is doing is first it tries to learn an efficient way to explore the environment. So it learns a set of policies that visits all the endogenous states. So in this problem, essentially means that it will learn a set of policies that can reach any place in the park in which we will place the pizza slice at. Right? So that's what I mean by learning a set of policies that visits all the endogenous states. And when we have this thing, we can also very easily design an algorithm that learns a near optimal policy, in the sense that there exists a reduction between the two, and we can use the PSDP algorithm, for example, to get 2 from 1. Okay, so let's understand how we make this, how PP is constructed, and its intuition is extremely simple. It's essentially a BFS algorithm, a breadth first search algorithm, plus some representation learning phase. So very much like in BFS, the intuition that I would like you to have in mind is that it operates in time step. It starts from the first time step, and then it slowly learns how to explore the environment and going through time steps incrementally. So psi here is essentially like the set of paths that PP learns. Okay, so let's try to describe the algorithm and give the proof simultaneously. The set of paths, the guarantee that we'll have here is that the set of paths is upper bounded by the number of states, of endogenous states. So so here in this type of problem, we imagine the scenario that the number of endogenous states, like the thing that we truly care about, is relatively small. Okay, right. So let's describe the algorithm and describe the proof. So much like in the BFS algorithm, we start by assuming that everything works inductively. What does it mean that it works inductively? Here it means that the cardinality of the set of paths that we hold is equal to the number of endogenous states at the previous time step. So for example, here, if we're trying if we're at age equal to 3, then we assume that at age equal to 2, we have this set of paths. We have 3 paths, because we have we have 3 endogenous states here, and that's the induction assumption. So let's assume that the induction assumption holds, and let's see what PP is doing. So again, we assume that at the previous iteration, we have an efficient way to explore the endogenous environment. Right. So the first step, PP extends all the paths from the previous time step by essentially taking all possible actions from each possible path. So graphically, it looks like this. If we have 2 actions from each state, PP essentially takes all the possible actions from each path. And so obviously we get a good exploration, a set of good exploration path on the 3rd time step. But does anyone see a problem here?
Not each part, but each state, right? Like for S6 at H3,
Yeah.
there is 2 different paths to reach each.
Yeah, exactly.
Okay.
Yeah, exactly. So the issue is that it's not surprising that Ishai knows that. So the issue is that we have 4 endogenous states here, but the size of paths is 6. That's something that we don't want to have, right? Because we want, like our ultimate goal would be to have that this set would be the same as S3, right? And obviously the reason for that is that we have multiple paths that reach to the same endogenous state, and that would result in exponential blow-up, right? And we want to get this set would be upper bounded by the number of endogenous states. So what we can do to solve this issue, obviously we can hope to be able to filter paths, right? So if we have 2 paths that reach to the same endogenous state, if we design an algorithm that can understand this and filter one of them, then we're done. So that's indeed the intuition for the PP algorithm. At the 2nd step, it eliminates paths that reach to the same endogenous state. And then we eventually end up with psi H.
So Yonathan, this is the answer to Danny's question. How are you giving information what is relevant?
Yeah,
right?
exactly. Yeah, by filtering paths.
It makes me wonder if you're not shooting yourself by eliminating states. Perhaps sometimes you have to split within a state.
Yeah.
Perhaps do it economically, but you sometimes have to split.
Yeah. So the guarantee here that we'll eventually have is that this set precisely can precisely reach to each endogenous state, and that the cardinality of this set is not larger than the size of the endogenous state. So there's a 1-to-1 correspondence. That's the guarantee that we'll have eventually. Obviously, the question is how we do it. Right. So let's imagine our problem again. We have 2 paths, and we want to decide whether we encounter option number 1, whether they reach to different states or they reach to the same state. Right. So let me explain about the mechanism that we develop, and let's introduce some notation. So we define a policy mu to be the policy that executes these 2 paths, pi and pi prime, with probability half. Right? It flips a coin a coin, a pair coin. If the coin is heads, then it will execute pi. If the coin is tails, then it will execute pi. And given this, we define the multi-step inverse model. This probability function describes what's the probability that we executed policy pi tilde, conditioning on the observation at the last time step, xh. And this thing would be like the key object on which we will build upon. So now I will describe two lemmas, and with which we can hopefully understand how PP is doing that. So the first lemma says that the multi-step inverse model is invariant to the exogenous noise. That we don't really need information on the exogenous noise to be able to predict the identity of the path. And this lemma is important, as we'll also see next, because it means that we can learn the multi-step inverse model if we have access, if we assume realizability. And the second lemma says that we can essentially construct delta here, which is a function of the multi-step inverse model, and from delta we can directly read off the solution to our question. If delta is 0, then pi and pi prime reach to the same state, and if delta is 1, then they reach to a different state, right? So ultimately, if we would have access to delta, we can directly decide about our question. So putting these two things together, first, with lemma 1, we know that we can learn the multi-step inverse model with only logarithmic number of samples in pi. And then with lemma number 2, we know that there's a margin, so we can essentially approximate delta up to a finite accuracy, say 0.25, and still be able to be correct with high probability. All right. So yeah, PP essentially is solving maximum likelihood and calculates empirical expectations to perform the path elimination in a provably correct fashion. Right. So I wanted to show the proof, but we don't have time, so let's keep it. Right. So in terms of sample complexity guarantee, we show that PP gets the thing that we hope for. We get the logarithmic dependence in pi. Yeah, and we also did a couple of extensions. We show that PP is robust to perturbations. That is, we don't really need to assume that stuff are deterministic. Also assuming near determinism is fine. And as I said before, we can take this result and construct a Paccarel algorithm from this result.
So the place where you actually use these like inverse mapping between like observation and state is only when you're doing the path elimination?
So yes, and specifically it's only when you're calculating the MLE, the maximum likelihood, when you use a convergence guarantee on the maximum likelihood, like a finite sample convergence guarantee.
I see. And kind of like this level of the algorithm to do the maximum likelihood, you're just kind of enumerating over all of capital thing.
Yes. Yeah, so because MLE, like, broadly speaking, you can't really solve it.
So unless if it has structure, then maybe it's
Exactly. Yeah. So we assume that we have some oracle that can give us the MLE. Right. So yeah, so let's just flesh out these results. So we also did a couple of extensions. We studied 2 extensions to this model. First, in this paper, in this code submission, we removed the deterministic assumption on the endogenous part of the state space. However, we did introduce a representation assumption that the feature vector can be decoupled into an endogenous and exogenous part. And then we derived some log the upper bound, which is also the thing that we were hoping for. And similarly, we studied a continuous LQR setting and defined what exogenous noise means in LQR. And we got much similar upper bounds, which look really like sparsity results in supervisor. Yeah. And in terms of some practical some, and in terms of what we tried out in practice, here we see, for example, we compare PPE to other algorithms. We showed that PPE, which is this line, that's the horizon of the problem, can solve this problem, whereas other methods dramatically fail. And here, that's an additional extension that we make. That's our algorithm, the ACRO algorithm that is built to filter the exogenous noise. And we also see that other methods dramatically fail in the presence of exogenous noise. And that being said, there's still an open question toward this direction. And the open question is essentially, can we get this log phi guarantee that we hope for without further assumptions? And that's something that I don't understand yet. I would be happy to explore it in the future. And also an impossibility result here would be extremely interesting because it would show some gap between reinforcement learning and supervised learning.
What was the assumption with the extent that you showed before?
Yeah. Yeah. So here, yeah, the assumption that we make is the representational assumption. So there's a representational assumption on the feature vector. And also here, there is a similar representational assumption that everything is axis aligned.
So the problem that corresponds to sparsity is basically solved in the more general.
In some sense, here, yeah.
So there are no extra assumptions.
There are a couple. There are a couple. Actually, there's one. There's a reachability assumption that we're not sure. There's some reachability parameter that I didn't want to mention here. But so that's like the key assumption, the reachability assumption.
In feature vector, you assume that you are told which is which coordinate depends.
No, exactly. So we don't know which coordinate is the endogenous and which coordinate is the exogenous, but we only know that this structure exists, much like in sparsity, that we know that there are K features that are relevant and D that are not relevant.
So you know the value of K?
You know the value of K. Exactly. It's yeah. It's only like first step that we've taken, but it's not clear to me whether you can do it without having at least like an upper bound on K. It's not clear to me. Yeah. So there are a couple of intricate questions along this direction. Yeah, okay. So I have 1 minute. So just flesh out additional results. Yeah, so we studied a sequential decision problem when the feedback is limited. And we also did a bunch of work on partially observed systems and some works on robust and safe reinforcement learning. And broadly speaking, all of these works are motivated by the need to resolve like practical issues. So to conclude, deploying reinforcement learning is hard, and we still don't know how to do it. And I think that we need close collaboration between theory and practice to really achieve it. It's going to take some time. One specific problem that we focus on, one specific structure of problem that we focus on here in this talk is reinforcement learning with irrelevant noise and with irrelevant information. I hope that I managed to persuade you that it's understudied, theoretically and practically important, and that our work provided the new provable algorithms, and we tried out a bunch of algorithms in practice. And yeah, to conclude, I think that theory can contribute for designing principles and provable algorithmic approaches in the future. And yeah, that's it. Thank you very much for your attention.
In the brief part on the vignettes, you said that these problems were motivated by practical problems.
Yeah.
Did you test them on practical problems?
No, of course. No, I'm kidding. But so we haven't. Here we have. Most of these works are theoretical works, specifically about the partially observed systems or POMDPs in general. Even like in practice, there are not a lot of works. We don't really understand how to solve these issues. And maybe one key issue is that we don't really have the proper domains. If we think about like DeepRL, there are like the standard domains of Atari games and and Jim, and which are fully observed, we don't really have an analogous Atari game with partially observed systems. So
I apologize for dwelling on this point, but on your first slide, you said that there were many successes of in robotics.
Mm.
The sense that I get over the last year or two is that there is big disillusionment from the marriage between RL and robotics.
maybe
If you know specifically of successes, I'd be very glad to hear.
I can share with you a couple that I'm familiar with, but maybe my definition of success is different.
Okay.
And yeah, so maybe we can define what success is.
I'd be glad to hear.
Yeah.
You don't have to do that.
Yeah. Yes.
So going back to the medical motivation that Sivan raised, in practice, maybe the assumption of Markovian process is a good approximation, but what would happen is that there will be, say, many features that are collected for patients.
Yeah.
And some of them will be very relevant, and the relevance will decrease. So there will not be a clear threshold, like in your case, between the really important features and everything else that is really relevant, but it will be more gradual. So you think this kind of theory could be also maybe extended in this direction, where you will tease out the most relevant features.
Yeah, that's also kind of related to causality, maybe a bit, right? Because maybe the irrelevant feature, they're correlated to the relevant, and then we ask questions: what happens when you go to a new environment? I think there are many questions towards the direction of healthcare, and these work specifically, I think that maybe this line of work is related to healthcare, but I wouldn't say that it's really practical. It's more theoretical line of work, in which we try to understand this problem a bit better. Yeah, I think so. This line of work, I wouldn't say that it can be used to really attack health problems. But yeah, I think that when it comes to health problems, probably the thing that is the most crucial is to really focus on this set of problems and try to understand the structure that we care about. And for example, if we have, if there are features that are not important, but you try to deploy the algorithm in a new environment, that requires, in my opinion, to really study this type of problem of generalization between environments. If I hope that I answer your questions. I'm not sure that I have.
Questions? Okay.